All right, it just said that my speaker is not working. Can someone talk to me? Can anyone hear me?
I can hear you fine.
I hear you.
Okay,
hear
I
you.
can hear you too. I went to record and it said that my speaker was not working properly, so I don't know what the crap that's about, but all right, let's try this again. Oh, I am recording. What the hell? All right, I'm recording. Hello, welcome, Astronomy 1020, to the second part of lecture number 10. Today, we investigate the cores of stars and compare them against one another. What is our working definition of a star in this course? Does anyone remember? We did this last time. Come on. Help me. Our working definition of a star. You're muted, Christopher, if you're talking to me.
Ball of plasma in fusion.
A ball with fusion, right. A ball with plasma and fusion in the core. Today, we tackle the fusion. That's today's work, okay? Next week, we'll take a little break from stars, but today we get into the meat and potatoes. Hey, I need to make an announcement before I forget. Well, one is that I still need to grade your homeworks. The second is I have friends that are coming from out of town today, and I think they're going to buzz me during this lecture. So if my phone rings, I have to just take it and push a button, and then there shouldn't, actually, I gotta make sure my door is unlocked. Okay, so let's start by talking about different mass classes of stars, okay? End class early. I'd like to do that. I would, I really would. Wait, why am I sharing? I don't want to share. I want a full screen. Okay. You guys know your spectral types of stars, of course, right? What are the spectral types of stars?
O, B, A, F, G, K, M.
I like it. Let me choose some appropriate colors. F, G, K, F. When these spectral types are really about the surface temperature of a star, and if you look at the HR diagram with me, you'll quickly realize that spectral types are what we call degenerate in mathematics. A degenerate function is one in which there are multiple possible values for the same coordinate. For instance, if I chose a spectral type G star, I would discover that the sun is a spectral type G, but so is Polaris. And these two stars are not the same type of star whatsoever. The sun is what we would call a main sequence star. It resides along the main sequence of the Hertzsprung-Russell diagram. Polaris is a red giant or a supergiant, depending on how you want to look at it. But if we focus just to stars along the main sequence, as we will at the beginning of our day, you will discover by studying binary stars that there's a tight correlation between the spectral type of a star and its mass. Higher mass stars are the O and the B ones. Lower mass stars are the K and the M stars. Sun, Sirius, and others are somewhere in the middle. It's going to turn out that what a star does during its lifetime, and in particular, what type of elements it confuses, will depend upon its mass class. And we're going to now break these stars down into three general types of star. The stars that are, let's see if A constitutes a high mass star. It might be, it's somewhere around 8 solar masses. So A doesn't quite make it there. So the O and the B type stars are going to be an example of what we would call a high mass star. And O and B types, as long as they're on the main sequence, of course, they can have a range anywhere from 8 solar mass units up to about 100 solar mass units. Now, that's going to seem like a pretty big range, but it turns out that there are many fewer O and B type stars than there are of the lower spectral types. Stars that are like A and Fs, which run from 2 to 8 solar mass units, we refer to these as intermediate type stars. We're not going to spend a ton of time on the intermediate type stars because it turns out they have some aspects of high mass star evolution and some aspects of low mass star evolution. So we're going to kind of focus on contrasting what high mass stars doing during their lives versus what low mass stars do during their lives in terms of fusion. And lastly, we have our low mass category. Do you guys remember what the smallest mass a star can have is? I always like to test you guys to see if you're remembering things. What's the lowest mass a star could have? The gene's mass is a condition for star formation. Sorry, Cam. The gene's mass is a thing we care about. No one can remember the lowest possible mass a star might have?
Is it 1.8
Lower.
solar mass?
Well, the sun is 1 solar mass unit, right? So the sun would violate that.
Wasn't it between like 1/100th and 1/1000 solar masses?
That's a teensy bit too small. Jupiter is 1,000th of a solar mass. Jupiter's not a star. It's a 1/10th of a solar mass. But these are numbers I'd like you to accidentally memorize, okay? So from, actually, I guess I should have done this backwards here. If I, 8 to 2 solar masses. Oh, wait, you know what? I screwed this all up. It doesn't matter. Okay, so low mass stars can go anywhere from 2 solar mass units all the way down to 1/10 of a solar mass. Under 1/10 of a solar mass, you cannot bring your central temperature up high enough for fusion. Now we're all going in the same direction there. Okay. Today, we want to talk about what type of fusion stars do, but it's going to turn out there's quite a bit of differences between how a low mass star evolves over time and how a high mass star evolves over time. One of the reasons is stars are these giant balls of plasma that depend upon gravity. But as you scale up the size of a star, these emergent properties develop, which are not intuitively predictable. We can only figure out how they work by doing complex computer modeling of the interior cores of stars. You guys may not realize this, but the people who work on analyzing stellar interiors are some of the same people who work at Los Alamos Labs and do research in nuclear fission reactions for atomic weapons.
10 minutes for Walmart, buddy.
Hey, who are you back there? Let's mute.
You're in class as you're playing Fortnite.
Is that you, Austin?
Oh, sorry.
Did you shut
I
that?
realize.
Thank you. All right, go back to your video game. You're clearly disengaged. Okay.
No, it's Tyler. I'm slightly engaged.
Okay. Okay, slightly engaged. I'll take it. I'll take it. Anyways, the point I'm trying to make is some of the codes for the interiors of stars are actually state secrets that are tightly guarded by the military. Because if you know how to model the nuclear fusion reactions inside stars, they also apply to atomic weapons. So a lot of research in stellar interiors is actually done at Los Alamos National Laboratory. It's kind of interesting. In any case, studying stars is a peaceful use of our nuclear knowledge, and we'll focus on that today. It is cool. Hey, you could just Google it. No, some of them you definitely cannot Google. I want to show you a picture that I might have shown you before, just to kind of wet your whistle here and get you thinking about why stars of different masses might behave differently. This is a rough and ready idea about what we would think the interiors of a low versus an intermediate, well, kind of intermediate, versus a high mass star would look like. Let's make sure that you remember the layers of our own sun, because if you cannot remember the layers of the sun, then you're not going to understand anything we do today. What's the outer surface layer right here called?
Photosphere.
Good. How about this zone here?
Convection?
Good. How about here? I'm going to test you on this, you know.
Radiation.
Good. And then this is the nuclear core. How does the interior of the sun differ from a very low mass star? What's the first thing that you notice here?
There's no yellow layer.
Right. And the yellow layer, Kaitlyn, is called
I totally did not hear what he said.
The radiation zone.
Radiation.
the radiation zone. So there's a meaning to this. Okay, that's fine. The yellow layer. Why is there no yellow layer? Why is there no radiation zone? I get, you know what? Do you guys know? So here in this part of the, oh yeah, Arunsak, take a guess.
It's because there's not enough fusion going on to give off the radiation.
Whoa. Let's slow our roll. Fusion only
Yo,
can
my bad,
take
my bad.
place- Fusion can only take place at the core of the star. These layers are not hot enough for fusion to take place in. Maybe that's a good thing we're talking about this. Let's get that straight right away today. The only place fusion can take place is right at the core, okay? These layers are not hot enough for hydrogen to fuse. All right, look. The reason a star switches over from radiative transport to convective energy transport is because this layer of the star is like 100% plasma. There's no electrons bound to the atoms. And if you think about it, I don't know how to do this. Let me just draw a little cartoon picture on the board for you guys. When hydrogen gas is in the plasma state, you have a sea of free protons and you have a sea of free electrons. And they're all kind of bopping around together like ping pong balls. Photons cannot be absorbed by plasma, not easily anyways. Usually what happens is the photons just kind of ricochet and bounce their way off the particles in something called a random walk. That means the photons are carrying the energy through the interior of the star. Once you get to cooler layers of the star, as the temperature lowers, you suddenly hit a wall in which the electrons are now bound to the nuclei. And once electrons are bound to the nuclei, they become very absorbent to photons, absorptive to photons. So the photons can actually get captured by the atoms. What starts to happen then is if you look at all your tiny little atoms, they start absorbing this wall of photons and they begin to bubble up and turn like a hot air balloon that rises. So in a kind of awkward, goofy way, what you're seeing is you're seeing where the star totally turns into a complete plasma. Here it's 100% plasma. Here it's some mixture of neutral gas and plasma. So what does it mean if I see that a low mass star is convective all the way to its core? Just kind of free associate with me here. What's that telling you?
There's just no plasma there?
Yeah, like this star is so cool that it probably just barely ionizes. So, okay, I can't really get behind that. It's not that there's no plasma there, it's just that there's some neutral gas there. Probably the star only gets to 100% plasma just as you get to the core. And keep in mind, we're going to need to be at 100% plasma for fusion to occur. Okay, was that Kevin that I just heard in the background there? Or is that Devin?
That was me, Paul.
Oh, Paul. Sorry, Paul. I'm trying to get used to the disembodied voices that I hear. Paul, if you'll keep working with me here, buddy, what does it mean about the high mass star? What do you see going on here?
Majority of it is made up of plasma.
Yeah, and there's no convection zone whatsoever. It's radiation scattering off of particles all the way up there. But holy shit, what's happening here at the core? There's something wacky going on. Paul, you're doing such a good job. Why don't you
Oh,
keep going?
still me?
Why not?
The convection is occurring in the core along with the fusion.
Can you imagine why that's happening? Why would convection be happening at the core? This might be too much, but
The
Take a
way
guess.
the plasma is pushing it down.
what's happening is it's going to turn out that these high mass stars do a different type of nuclear fusion in their cores. And these stars are producing so many effing photons that it's turning the star turbulent and convective again, not from absorption of photons, but from radiation pressure. Do you guys remember that I did that cool demo with the Crookes radiometer where the photons blew the little windmill around? Probably they're generating so many photons that those high mass stars are literally threatening to shine themselves apart. If you went a little bit over 100 solar masses, this turbulent layer would go all the way out to the edge, and then bam, you'd have Eta Carina right there. You'd have this just disruptured star because it shined itself apart. That's when the star achieves its so-called Eddington luminosity. Okay. The idea of showing you this picture is to get you to meditate on how even the interior structure of low, medium, and high mass stars is different. Let's start with what we know about our own sun. Actually, last time, there's one other thing I want to say that I think is important here. I want to talk to you guys about something that professional astronomers know as the initial mass function. And the initial mass function is the technical term for astronomers trying to answer this question about when stars form. Does nature prefer to make big fat stars or little skinny stars? The answer is the little tiny stars, okay? It asks how many stars of spectral type X. It could be OB a fine girl kiss me. Let's say, I don't want to be confusing here with the letters. How many stars of spectral type question mark are formed each year? Well, year probably isn't the best term. I need a better marker here. It turns out that 7-Eleven sells dry erase markers, and that's a fact for which I'm very grateful this morning. Okay. Do you guys remember how many stars are in the Milky Way galaxy? What do you know? Tell me what you know.
Trillions.
Yeah, well, it turns out it's closer to
At
100
least
billion.
100 billion.
Yeah, it's a couple of hundred, maybe 300 billion. I lied to you the first day. I told you it was a trillion. Not because I really cared if you knew the number of stars in the galaxy, but because I wanted to see if you knew how many zeros were in a trillion. So I kind of told you a lie. Now I got to fess up. It's more like 300 billion or so. Okay, anyways. It turns out that the Milky Way galaxy only forms roughly one star per year. So typical star formation rates, one star per year. Now, if you're thinking that the galaxy has, I no longer trust you. You shouldn't trust me. The study of physics is the study of lies all the way down, okay? Listen, the Milky Way galaxy forms one star per year. That may not sound like a lot of stars, but keep in mind a year is nothing to a galaxy. Galaxies evolve over billions of years. In 100 years, you create 100 stars. In 10,000 years, you create 10,000 stars. And in 1,000,000 years, you create 1,000,000 stars. 1,000,000 years is a short time for the evolution of a galaxy. So we consider one star forming per year to be a healthy star formation rate. So let's not say how many stars are formed per year, but what if I waited, say, 261 years? If I waited 261 years, how many, why 261, Caitlin? Because it's going to match the graph that I have. I saw your eyebrows furrow. Or maybe it wasn't about that, but I want to show you guys this picture here of the initial mass function. Where is it? Come on. Okay, slide 65. If I waited 261 years, I would discover that for every one O star that nature creates, nature will form roughly 10 spectral type A stars, 50 stars that are like G types, and 200 stars that are like K or M types. So nature produces many more low mass stars than it does high mass stars. Do you guys remember the homework question where I asked, suppose we formed a star cluster from all of these stars? What color would the star cluster be if I mixed all of these stars here together in these proportions?
Probably blue.
Yeah, this guy is going to outshine all the rest of them. But this guy also lives for a much shorter time period. So when it goes supernova and pops, eventually the clusters will look older and redder. That's why the so-called globular clusters have so many low mass K and M type stars, because their high mass stars have all supernovaed and died off. Remember also that on the day when a star forms, we have a, oh, by the way, I guess we should take this as a note in case you're interested. For every one O type, you get 10 A types, 50 G types, and 200 M type stars. So this is the result of our studies of star formation. We discovered that nature makes more small stars than it makes small and dim and low mass stars than it makes high mass stars. On the day that a star forms, it begins a process of fusing hydrogen into helium, and that's when it becomes a so-called ZAMS star. Does anyone out there remember what ZAMS stands for, this acronym?
Zero age main sequence.
Yeah, thank you, Christopher. Zero age main sequence basically means it's the star's birthday. It was just born. And when a star borns, it undergoes its first round of fusion. The fusion that it begins to undergo is hydrogen, to helium fusion. And the hydrogen to helium fusion will place the star right along the main sequence. So depending on what its spectral type is, the star will kind of end up here along this diagonal line. And that's where it begins its life as a main sequence star. I call this the main sequence. Well, we got it right here. This is luminosity and this is temperature, right? Do you guys remember what method the sun uses to fuse hydrogen into helium? We had a whole lesson on this. Come on, someone's got to know. The name of the nuclear, pardon?
Is it fission?
No, fission is when, whoa. Okay, we got to slow our roll here. We got to go back and relearn what we've already learned so that we can learn something new that we'll forget later, okay? So let's start by reviewing the difference between fission and fusion. I think we have to slow this down a little bit here. Fission is different than fusion. Fission is when you break a big fat nucleus like uranium-235 apart into daughter nuclei and release energy. This is what the atomic bomb that we dropped in Hiroshima is based on. This is also how nuclear power plants work. Fusion is what stars do. They fuse smaller nuclei into bigger nuclei, releasing energy and leaving no radioactive byproducts. I wasn't asking you whether a star does fission or fusion because I thought you already knew a star does fusion. I was asking you a next level question, which was, what is the name of the nuclear reaction sequence that the sun uses to fuse hydrogen into helium?
Was it proton?
That's right. The proton-proton chain. Very good. Was that Paul again, or
No, it was Kevin.
Jesus? I can't tell you guys apart. Okay. Thanks, Kevin. The proton-proton chain. Let's take a look at a review of the proton-proton chain, because apparently most of us have forgotten it. Okay. The proton-proton chain has 3 steps in it. First of all, remember that the way fusion works, we probably should draw a little diagram here, is in the core of a star, you have a completely ionized plasma, right? So you have these 2 protons, and well, you have more than 2 protons. You have like a bazillion, trillion, million photons. Sorry, not photons, protons. And they're all moving at such high kinetic energies that they are going to travel on a kind of collision course. Now, normally, the collision of 2 protons is actually very similar to what happens when you try to push 2 magnets with the same polarity together. As the 2 north poles move towards one another, they feel a magnetic repulsion that pushes them off to the side. Have you ever done this, taken some fridge magnets? I'm sure you have. Every kid has done this. You push them apart, right? So imagine that's happening, except now it's due to electrostatic forces, okay? So these 2 protons are flinging towards one another, and they're deflecting away from each other. During the deflection, they get to some critical distance called the impact parameter. And if the 2 protons can get close enough, a new force of nature will take over called the strong nuclear force. The strong nuclear force is a creepy, mysterious, fundamental force that binds protons together. You might actually think of the strong force as being kind of like, it's almost like Velcro in a way, where if you can get these 2 protons close enough, they've got to get really, really, really close. Then that strong force will take over and will glue the nuclei together. The strong force has some strong, no pun intended, some strong differences between itself and a force like magnetism or gravity. Electromagnetism and gravity are long-range forces that can act over the size of a star or the size of a galaxy. But strong nuclear forces are only potent in a very short range, comparable to the diameter of a proton. So you got to get these things flung at each other really hard and fast for the strong nuclear force to take over. You should recognize that the strong nuclear force is the force that governs fusion reactions. Let's remember how the sun does it, and let's just take a trip down memory lane. There are 3 steps to the proton-proton chain. In step 1, 2 high-speed protons collide with each other to make this nucleus here. It's called a deuteron. It is the nucleus of deuterium. That's still hydrogen, but it's heavy hydrogen. It's a hydrogen with 1 neutron attached. In the process, we emit some antimatter in the form of a positron, and we also emit some neutrinos. Those are those little light massless practically massless particles that can fly right through the star. The deuteron then collides with a proton to make helium-3, emitting a gamma ray. And then, after this reaction happens twice, 2 helium-3s will collide with each other to make a proper helium-4 nucleus. The net reaction is that 1, 2, 3, 4 protons are glued together to make a helium nucleus, and they emit 2 gamma rays in the process. Because this is going to get a little bit confusing, I think what we should do is summarize all of chapter 17 as a kind of big graph. And the graph will label the different types of fusion that we would expect to see in stars. My idea is that this will be a very useful study tool that you can memorize and that will help you answer many questions during the exam. So let's go ahead and, by the way, the study of nuclear fusion in stars is called nucleosynthesis. There's a $10 vocabulary word for you. Let's write it down. So we're going to make a table about the nucleosynthesis in stars. And play along with me here if you have a ruler. Hold on, I'm getting texts. And so make maybe 1, 2, 3, 4, 5 columns. And I'll tell you what the categories are first. So our first class of star, this is going to be, let's see here. This will be the mass class or the star type. And what we're going to be trying to do today is we're going to contrast the type of fusion a star does during its main sequence evolution with what happens in later stages when a star turns into a red giant, in some cases a blue supergiant, and then lastly, this will take us past our lecture in relativity, but we'll talk about the death throes of a star as well. And we'd like to compare our 3 types of star. First, at the bottom, we'll do the low mass stars. Which is 0.1 to 2 solar mass units. We'll contrast that with intermediate mass stars, which run from 2, bloody hell, hold on, 2 to 8 solar mass units. And then we'll do high mass stars, which go from 8 to 100 solar mass units. Now, you guys might be tempted, if you're feeling cynical, to think, you know what, Brendan, this is some wacky esoteric shit about the interiors of stars, and I don't care because I'm not interested in nature and beauty, and I don't care about thinking about abstract stuff. I'm just curious about when the next PS5 drop is going to happen. Okay, and that's a valid perspective. But I want to tell you that what's happening inside the cores of these stars is more intimately connected to your day-to-day life than you may realize. Right down to why does it cost so much money and why is it so difficult to manufacture enough of these fun electronic gizmos that I like to spend my time doing. And by the way, before you think I'm a cynic, I like to play me some video games just as much as the next fella does. But I'm also interested in nuclear fusion in stars, okay? Okay, so we've learned, like what? Like you want to talk about high mass star or low mass star nuclear fusion? Oh, actually, a friend of mine, well, there's a story behind that, but I'm not going to get into it. I won't tell you, it's top secret. Okay. Low mass stars undergo fusion by, so let's remember that what glues together the commonalities of all stars during main sequence fusion is main sequence fusion is always hydrogen to helium fusion, but it's not always the same way, okay? The proton-proton chain, which we just reviewed, that's the nuclear reaction cycle that low mass stars, including our sun, use. And remember that the net reaction is that 4 hydrogens fuse to make 1 helium and 2 gamma rays, okay? 4 hydrogens fuse to 1 helium and 2 gamma rays. That's the net reaction. As you raise the mass of a star, you also raise the central temperature of a star. Do you guys remember what the central temperature is needed to undergo fusion by the proton-proton chain?
15 million degrees Fahrenheit, I believe.
Not Fahrenheit. We don't use Fahrenheit. 15. Sorry?
Kelvin.
Yeah. Which is honestly kind of close to 15 million Fahrenheit because the differences are so minuscule. But so the central temperature is 15 million Kelvin. If you go to higher temperatures than this, nature will still fuse hydrogen to helium, but nature comes up with a different method of doing it. And it's got a kind of confusing name. It's known as the CNO cycle. And both intermediate and high mass stars use the CNO cycle. Wow, I'm dyslexic today. Okay. Let's take a moment to look over the CNO cycle and let's see how it works. I have a cartoon. So this is a cartoon with the proton-proton chain. The CNO cycle is more complicated. So I'm going to just kind of walk you through it, but I will not expect you. I expect you to memorize the 3 steps of the proton-proton chain because that's the cycle that our sun uses, and it's only 3 steps. I will not expect you to memorize the steps of the CNO cycle, but you do have to listen to me talk about it just this once, okay? So it's kind of a 6-step reaction with a lot of nuttiness going on. The first idea is that even though we're fusing hydrogen into helium, we're doing so by using that trace amount of 2% metals that we find inside of a star. And one of the most abundant metals, if you rank the metals by popularity, carbon, nitrogen, and oxygen are 3 of the most abundant metals that we find inside of a star. Carbon is going to turn out to become a binding site or a catalyst in the reaction that helps hydrogens fuse together. In step 1, I have a big carbon nucleus. It's got, let's see, 6 protons and 6 neutrons. And along comes a high-speed proton, which is the nucleus of a hydrogen. And the high-speed proton, bam, it whacks into the carbon. And when it does so, it adds an extra proton, which changes the element from carbon-12 to nitrogen-13. Nitrogen-13 is an unstable isotope of nitrogen. Normally, the proper isotope of nitrogen, the most common one, the stable one, is nitrogen-14. That has 7 protons and 7 neutrons to glue it together. Well, nitrogen-13 is unstable, and usually what it prefers to do is one of those protons will spontaneously pop, and it will disintegrate through the weak decay force, the weak nuclear force. It will transform itself from a proton into a neutron by emitting a positron and ejecting its positivityness. I mean, positrons are really weird because they're basically like the mass of an electron, a little microscopic dot, but it carries all of the charge associated with this particle. So the positron radiates away the positiveness, and the neutrino changes the mass a tiny bit, and suddenly you've transformed your proton into a neutron. Now the element has become carbon-13, an unstable isotope of carbon. Carbon-13, pow, gets whacked with another hydrogen, and it becomes a proper nitrogen-14 nucleus. Oh, I should have mentioned that there was a gamma ray emitted here in this step. There's also a gamma ray emitted in this step. So far, it looks like what we're doing is we're fusing carbon into nitrogen, but there's something else that's at work here. It's a trick, okay? In step 4, nitrogen-14 gets whacked by another hydrogen, and it emits a gamma ray. It now becomes an isotope called oxygen-15. Oxygen-15 then spontaneously decays through the weak nuclear force, and transforms a proton. Actually, it looks like it's transforming an, all right, whatever weed smoking artist drew this picture clearly had smoked a little too much weed that day. You will notice that the proton is supposed to turn into the neutron. And I never noticed this before, but they accidentally got their colors wrong. They show a neutron turning into a proton, but that doesn't make any sense. If it's going from oxygen to nitrogen, yeah, that's crazy, right? No, that's totally crazy. CNO. All right, that should be red and that should be black. I never noticed that before, but they screwed that up. Okay, oxygen 15 decays to nitrogen 15, and the nitrogen 15 gets hit with one more proton. Now at this point, nature could iterate and change this nucleus to oxygen 16, but nature doesn't do that. What nature does is it poops out a little helium nucleus here, and the original atom, carbon 12, remains left over. So in a way, this was kind of just like a little glue trap to capture 1, 2, 3, 4 protons and turn them into a helium nucleus. The net result is that 1, 2, 3, 4 protons fuse to make one helium, but it emits, wait for it, 1, 2, 3 gamma rays. Why does that matter? Because the gamma rays are the energy that powers the star. Class, if I go from 2 gamma rays per reaction up to 3 gamma rays per reaction, what increase in energy yield does this reaction have? Who's good at math? Who works at a bank? If I go from 2 photons per reaction to 3 photons per reaction, what is your increase in efficiency? Someone's going to chat me the answer here. Oh, you got fired? Jesus, Austin. Oh, God. All right. Well, then that means learning your stuff in school is even more important. Wait, hold on. Someone had the right answer. Was that Cam? Yeah, Cameron recognizes this as a 50% increase or a 50% yield, right? So keep in mind that if we go to 4 hydrogens, 1 helium plus 3 gamma rays. Guys, imagine if you could get a 50% raise at work, right? That would be insane. That would be huge. My life would be fundamentally changed if I got a 50% raise in my salary. I would be an even bigger debaucherous degenerate than I am today, okay? So I would love to make 50% more money. I would like to have 50% more cookies in my cookie jar. If a star goes from 2 gamma rays to reaction per 3 gamma ray, you should not think of it as, oh, you're just getting 1 extra gamma ray. You should think of it as a 50% yield or a 50% increase. Class, what might that have to do with the picture that I showed you of those 3 stars at the beginning of our lecture? And maybe we could talk to Paul if he's still listening. Paul, how does this relate to the discussion that we were having about the cores of high mass stars?
Those high mass stars are creating even more gamma emissions than the low mass stars, so they got more energy.
And what is that? So I guess what I'm trying to riff on you with here, Paul, is that sort of helps explain why the inner cores of these high mass stars are turbulent, doesn't it? Because they're producing so many photons that the pressure of just pushing those photons out through the star is causing the gas to become turbulent. They're basically like a big egg beater that is mixing the core of the star. In a way, you can see the difference in the nuclear reaction right here in this picture because those extra photons are pushing too hard against the star. Okay, cool. How long, let's see if you guys remember other things. How long will the sun live as a main sequence star? That's something I would expect you to know. What is the total length of time a G-type star exists in the main sequence stage. We sometimes call it the lifetime of the sun.
$10 billion years.
10 billion years. How about an O-type star? How long do they? So let's actually write this down. Well, there are differences in age here. A low mass star might live for 10 billion or more years. Christopher, do you remember how long an O-type star will live for?
I think a few 100 million.
Barely even. Probably more like 50 million years or something. Which is obviously a way shorter lifespan, right? Let's first talk about what will the sun be like if we could go 5 billion years into the future to where the sun runs out of nuclear fusion. You guys may remember that I told you there was this Danny Boyle movie called Sunshine. Oh, okay, Chris, I got you. And in this movie Sunshine, they imagine a future where the human race, the sun is dying, and they have to go and restart nuclear fusion in the sun to keep the Earth from sort of getting singed or something. It's kind of a cool and slightly scary movie. You should watch it sometime. It's called Sunshine. In any case, what will the interior of the sun look like? Well, I don't want to lose all of this, so I might have to draw this on my my whiteboard here. Okay, let me draw some circles for you guys, okay? Let's imagine we could zoom into the core of the sun. So this is just, we're just going to draw the core of the, what the hell? Text, okay. The core of the sun. And the core of the sun is maybe the inner 15 or 20% by radius, okay? And let's start by using a sort of red circle on the outside. So here's the core of the sun. And in this core, we're fusing hydrogen into helium. And over time, we develop oops, sorry. Can I draw one circle on top of another circle? Yeah. There we go. Okay. So, bear with me here. The core actually has multiple layers to it. In the outermost layer, you have a layer of hydrogen to helium fusion that's happening by the proton-proton chain. But I want you guys to remember, what is the difference between a hydrogen versus a helium nucleus, right? In a hydrogen nucleus, basically you have one proton. But a helium nucleus is 2 protons and 2 neutrons, right? Since protons and okay, I can't really draw with this fucking thing. Let's undo this. I don't like this. All right, let's just go to my drawing tool. So I have 2 neutrons and I have 2 protons, right? If a proton and a neutron are roughly the same mass, that means the mass of a helium atom is 4 times greater than the mass of a hydrogen atom. You have 4 nucleons instead of 1 nucleon. Check a look at this. This is a stone, a piece of granite that I found at Goosewing Beach. And I liked this stone. It made me happy, okay? A stone has 3 times the density of water. Water has a density of 1 gram per cubic centimeter. A stone has a density of 3 grams per cubic centimeter. What would happen if I dropped this stone into a pool of water?
It sinks to the bottom.
It sinks to the bottom because it's 3 times denser. Here, my friends, our helium nucleus is 4 times denser than hydrogen. What is it going to do? It's going to sink towards the core of the star. So this is what we sometimes call the interior of the core of the star is sometimes called an inert helium core. The reason why we call it an inert helium core is all of the fusion is raging around on the outside of the star, but on the inside of the star, all of the helium starts to sink to the bottom, but it's not yet hot enough for the star to undergo helium fusion. The result is you get this big degenerate lump of helium in the core of the star. And I need to talk to you guys about degenerate gases. When hydrogen fuses into helium, it produces gamma rays. And the gamma rays are radiated out of the core into the radiation zone, and they provide the central pressure and temperature that a star needs to support itself. But a star is not like a solid piece of wood with a uniform density. Sorry, it's a little noisy outside. I'm going to just close over my window. Sorry about that. I want to show you guys something. It's a technical graph. Usually people don't like that. But I want to look at the so-called, whoops, sorry, the mat. Can you guys see my Google right now? No, you cannot.
No.
All right, that's, I can only share one thing at a time here. Let's share my screen. I want to look for a graph called, I think I have it in my slideshow, but the mass profile of the sun. This is the kind of graph that an advanced student would look at in a stellar astrophysics course. I want to show you this. Open that in a new tab. I want to open this in a new tab. Okay. It takes a minute to understand how this graph works. First of all, you guys should realize that a star is not like a uniform block, but a star basically has a profile where it changes. All right, so this is one for density, okay? And I want you guys to look at the density of the sun. So this is the radius of the sun. We're going from the very center of the core all the way out to 1 solar radius. And here you can see the convection zone, the radiation zone, and the core. You will notice that the density of the star is not uniform, but it changes dramatically as you go from the outer edge towards the core. If water has a density of 1 gram per cubic centimeter, the outer layer of the star, the photosphere, it has a density of like 10 to the minus 7, 1/10,000,000th that of water. It's just a very tenuous, low density gas, even lower density than the air in the rooms that you're breathing. When I get to about half the radius of the star, it's basically gotten up to the density of water. But once I get to the sort of inner 20% or so, where we enter the core of the star, the density suddenly goes up to maybe 20 grams per cubic centimeter. And at the core, the central core, the density is 100 grams per cubic centimeter or more. There's not even an atom on the periodic table that has that density. You're smushing all of this matter in so intensely against itself. Because of this, the mass that is contained within the star, hardly any of the mass of the star is out here, and up to 50% of the mass of the star is actually contained inside the core. And I'm not sure you guys appreciate what that means, so I'm going to try to show it to you. Let's see if we can find the mass. By the way, the temperature also goes up too, right? This is worthwhile looking at because you can only get hot enough for fusion once you get into the 15 million Kelvin range. So all these layers are not quite as hot. It's about 6,000 Kelvin out here, but it starts getting into 10 to 15 million Kelvin up at the core, okay? I want to see if they have one for the mass profile too. That's what I actually want. Not density, but I would like mass. Oh, here we go. This is going to be kind of confusing for some of you, but let's try it anyways. Learning to understand graphical data is one of the hallmarks of being a scientifically educated person. the mass of the entire star is contained. Oh, this is density, radius. Oh, the interior mass is on this axis. Okay. The entire mass of the star is contained at 1 solar radius. By the time we get to the core, which is close to 20%, you will notice that maybe 30 to 40% of the mass of the star is contained inside the core. 30 to 40% of the mass of the sun. Guys, if I had a big ball of gas or plasma that was 0.4 solar mass units, that's significant enough in itself to be considered a star. Who knows their spectral types? What would be the spectral type of a star whose mass was 0.4 solar masses?
A K or an M.
Very good. Probably a K, Kaitlyn, because the M's are usually a 10th, right?
K for Kate.
I was actually just thinking that. All right, Jinx. K for Kaitlyn. No, listen. What that means, dudes and dudettes, is there's a star in my star, okay? There is a star inside the freaking sun. Like, the interior core of the star is itself massive enough where if you stripped out the outer layers, that would still be a star. But here's what's kind of creepy about it. Normally, it's fusion that helps a star maintain hydrostatic equilibrium. But what the hell is going to keep this interior lump from collapsing into a black hole? See, what I'm worried about, what you're not worried about, but what I am worried about is, how can this star maintain hydrostatic equilibrium when there is no, oh, there's my friends. Okay. How can this star maintain hydrostatic equilibrium when there's no fusion going on inside there? The answer is a weird, wacky, and freaky thing that we call degeneracy pressure, okay? It's time for you guys to have a little lesson about degeneracy pressure. First thing we're going to do is we're going to start by looking at a normal gas, an ideal gas, okay? I think my lecture on the sun might have a model of a normal gas. Basically, I have that picture or that animation here in slide 19. My mouse is missing. Whoa, what's going on there? Let me see if I can function F517. Okay, good. Oops. What was it? Yeah, here it is. A normal gas, the gas that we find in the outer layers of the star, and even on the core itself, and to some extent, obeys the ideal gas law. You'll remember that the ideal gas law means P equals NKT. It's a relationship between pressure, density, and temperature. And in an ideal gas law, you kind of have like a bunch of ping pong balls in a box. They all travel in a straight line, they bump into each other, and they bounce off one another. What I would like to point out about our ideal gas is that the interparticle separation, the separation between two protons or two electrons, is many, many times greater than the size of the particles themselves. Hello? Hi, welcome. Make yourself at home. I'll hang out with you guys in a bit. Okay, so the interparticle separation, the separation between one proton and another proton, is maybe hundreds of times greater than the size of the particles themselves. But ask yourself, what would it look like if I started to smush this gas together more and more and more uncomfortably? As you compress the gas beyond its point of comfortability, the gas will suddenly start to appear more like a beehive or more like a carton of eggs, where the interparticle separation, and here I'm going to try to use my whiteboard to draw this. So let's clear all this, clear all the drawings. So here's a picture of a normal gas where the particles are all kind of separated from one another. But once your gas becomes degenerate, okay, your particles will all start to kind of squeeze against one another. All right. I'm not really good at drawing on this thing, but I'm going to try. In a degenerate gas, the interparticle separation starts to become so small that it becomes comparable or even less than the diameters of the protons themselves. And when this happens, the gas will completely change its behavior. You have no experience with such a gas. In order to press particles this closely against each other, you need absolutely extreme astrophysical conditions, the kind that you would never find on planet Earth. Not even in the core of Earth are particles being smushed this harshly. Maybe in the core of Jupiter, but not in the core of Earth. And so you're basically smushing all of these protons against each other. And when the gas becomes degenerate, it behaves completely differently than an ideal gas. In a degenerate gas, pressure does not depend upon temperature. Now, do you guys remember what temperature measures? What is temperature? How do we think about temperature when we, yeah, Arunsak.
The speed of particles.
The speed of the particles. And how would you think of the pressure? You did good with speed of the particles. What would be the simple equivalent description of pressure? Pressure is the force of the particles smashing against each other, okay? Remember, pressure is force per unit area. If a particle bounces off a wall, it exerts pressure on the wall. Or it could just be the force of the particles smashing into each other. In an ideal gas law, usually the faster the particles move, the more pressure you have. That is ping pong ball logic, right? In a degenerate gas, the pressure of the gas does not depend upon temperature. It depends on a wacky property of quantum mechanics called the Pauli exclusion principle. The Pauli exclusion principle states that no two particles can have identical quantum states. They can't have the same energy. They cannot have the same momentum. You know what it basically means? Let's just let's dumbify this with some ping pong balls here. I had some. One cartoon.
Universe.
Sorry. Oh, I'm sorry. What did you say?
I was gonna make a joke about the singleton. I was gonna make a joke about singletons.
Oh, about singletons? Well, what's the joke? I want to hear it.
Yeah. How even the universe like prefers singletons over twins.
Well, in human populations, it prefers singletons. But when nature makes stars, it actually is kind of half and half about singletons versus twins. Isn't that right? What do you think there are more of in the universe, humans or stars?
Oh, stars.
Probably, yeah. I mean, I wouldn't say that about aliens versus stars. It's hard to know. There could be aliens around every star, in which case there might be more aliens than stars. I'm not sure about that one, but there's definitely more. Prove it. I'm trying to, okay? You know, okay, in quantum mechanics, you're not supposed to think of particles like protons and neutrons. You're not supposed to think of them as little balls like this because they're supposed to be wave packets or something. They have a wave-like nature. But let's imagine that a proton and a neutron, let's imagine they're like these little things here. What degeneracy pressure means to me is that the particles themselves are pressing up against one another and they have no more room to wiggle. In that sense, they're kind of like a bunch of bees doing a little beehive dance. The pressure of the star is being supported by the quantum mechanical repulsion of the protons and electrons smashing against themselves. In the case of a low mass star, let's look at my slideshow again. The type of degeneracy that prevents the sun from collapsing its core into a black hole is called electron degeneracy pressure. It's actually the pressure of the electrons smushing against themselves that supports the outer layer of the star. Okay, it's time for us to compare the sun as it was when it first formed to what the sun will look like 10 billion years from now, or even today. So when the sun first formed as a ZAMS main sequence star, the fusion was probably distributed all throughout the 20% radius core. But over time, as the star deposits more helium ash into the core of the star, you will get a bigger and bigger lump of helium, and the shell that can still undergo fusion will become thinner and thinner and thinner. And eventually it'll get to a point where you basically have used up all of the hydrogen that can be fused inside the core, and your core now becomes a big degenerate lump of helium that's holding itself together by helium gas. Now, what would you think would happen if you could suddenly turn off fusion in the core of a star? What would you expect the star to do? I mean, let's think about hydrostatic equilibrium. Hydrostatic equilibrium is a balance between two forces. Do you remember what those forces are? How does hydrostatic equilibrium in a star work? Hydrostatic equilibrium is what keeps the star's radius intact, or what keeps the star in shape. Maybe you need a picture of hydrostatic equilibrium. Remember this picture? Explain to me what's going on. What does this picture mean? Someone talk to me and enlighten me with their knowledge of hydrostatic equilibrium. I want to know that I'm talking to some enlightened people here.
So the outward pressure is less, like, yeah, the gravity is more than the outward pressure.
Right, because remember that at first the star has normal pressure. They should have drawn the pressure arrows in here, because this is where the pressure is pushing back against the star. I don't know why they drew it. You know, these weed smoking artists, man, you can't rely on them to make a good illustration. So the gas pressure is in here and it's pushing back against the star. But what this picture does not show you is that something has to support the pressure inside the center of the star. And what that is it's the nuclear fusion. All of those gamma rays, which are being generated through fusion, are heating the shit out of the interior of the star. And that's what's creating the thermal pressure that pushes back against gravity. What would you expect to happen if you turned off fusion in the center of your star?
It would collapse.
Yeah. Like what happens to your car when it runs out of gas? It slows down, it stops, it splutters, and it dies. You would expect that if a star ran out of nuclear fusion, gravity would take over and squeeze the star. When will it stop squeezing?
When it turns into a black hole.
Pretty much. That's actually the right answer, Arunsak, except our star, the sun, can never turn into a black hole, because what actually happens instead is totally screwed up and something that you would not normally predict. Instead, wait, can you see this? I don't think you guys can see what I'm doing here. Hold on. Share screen, share screen, share. Let's get out of this slideshow and let's go back to this slideshow here. Instead of the star collapsing, which is what you would assume would happen, the exact opposite of the star happens. The exact opposite of that happens inside the star. As you squeeze your fusion into a thinner and thinner little shell, the core of the star becomes disconnected from the outer layers of the star. Your book calls it a broken thermostat, but what it really is it's like two disconnected stars interacting with each other. First, the little K-type star that's inside the sun will start to squeeze down and it will start to collapse towards a black hole. But that paradoxically pours more fresh hydrogen onto your little nuclear nugget, and that creates an insane burst of fusion that pushes so hard against the star that it actually begins to expand the outer layers of the star. You no longer have a star, you have two disconnected objects. You have an interior lump, which is collapsing because it has no fusion to support it. And then you have this burst of fusion that's puffing out like a big hot air balloon, the outer layers, the outer envelope of the star, And this is when your sun will enter the red giant phase. As I've mentioned many times before, when our sun enters its red giant phase, its outer radius will swell to preposterous dimensions. I thought I had stellar death in here too. I must have closed it out. This is just a crummy little illustration, but this is basically what the sun is going to look like 5 billion years from now. Its outer envelope over a short period of time will start to swell out as the core develops. It will easily swallow the planets Mercury and Venus, and calculations differ. Some people say the outer edge of the sun will press up against the Earth and just roast the Earth to a crispy cinder. And some people say the outer envelope of the star will actually swallow the Earth, and we will just get subsumed into the material of the sun. Obviously, we better have a good escape plan before that happens. We'll work on that, okay? Now, the sun has entered its red giant phase. What do you think that's going to look like if we plot it on an HR diagram? Death by sun is how I'm trying to die. I'm with you on that, man. Death by sun is right up there with getting struck by lightning. That would be probably, if you're going to have to go, make it dramatic, right? Okay, so let's take a look at what I want to do for you guys is I want you to imagine plotting this on the HR diagram. Today, the sun is a spectral type G star, and it's located here on the main sequence. When the star runs out of hydrogen to fuse, the star will begin to expand, and you guys might remember that the radius increases diagonally to the right on an HR diagram. At this point, the sun will begin to move up what is known as the asymptotic red giant branch. It begins expanding, and let's see if you guys actually did pretty good on this last time. What's happening to the temperature of the star as it evolves up this branch?
It's going up.
False.
What? How is that
Yeah.
false? That arrow is pointing up.
But the luminosity is plotted on the vertical axis. Look, Kaitlyn, temperature is being plotted on the x-axis. If you mark the position here versus the position here, what is actually happening? Sorry, I need straight lines for this.
Okay.
Do you get it now?
Yeah,
So
I get it now.
Be careful, because these are the types of questions I might easily ask on a test, all right? Here, the star has a temperature of 6,000 Kelvin, but when it turns, by the way, Kaitlyn, this is why it's called a red giant, right? Because as a star cools off, it becomes redder. It's a black body, right? Now,
True.
Kaitlyn, if I instead asked what's happening to the luminosity of the star, what's the answer to that question?
That's going up.
Right. Wait a minute. How can its luminosity go up when its temperature is going down?
Because it's cool like that. Surface area. Yeah.
More surface area. If the star expands, maybe it's a cooler black body, but it has more panels of square meters at its surface to radiate away. That means if you're on Earth, you're fucked, because the luminosity of the sun is going to go up way above what is comfortable for most organisms. Yes, Arunsak. Did you have a question?
Yeah, I did. I wanted to say something. So the reason why it's getting bigger is because it's losing fusion, and therefore it's losing that gravitational pull inwards, and that's why the gas is going out.
I'm glad you asked this question, because it's really confusing. Arunsak, to understand the answer to the question, you have to understand that fusion is hyper sensitive to the temperature of the reaction. I think in one of my advanced books over there, one of my upper division or graduate level texts, I once read that the rate at which fusion reactions recur, the fusion rate in a star, is proportional to something like temperature to the power of 27. That means if you make a microscopic change in temperature, the rate of fusion just goes shitty bonkers, okay? Like for instance, let's imagine we doubled. Let's imagine that we doubled the temperature. We don't actually double the temperature, but 2 to the power of 27. Oh, you like shitty bonkers, huh? to the power of 27 is like, wait, what is this? That's 130 million, okay? So if you doubled your temperature, your fusion rate would go up by a factor of 130 million. Think about how stupid that is. So the reason why the star puffs out is because it's because of hydrogen shell fusion. Because now you have the contracting helium core. And what happens to gases when you contract them, Arunsak? What happens to a gas when you compress it?
They heat up.
Right. So you're compressing this thing and it's getting hotter and hotter. And as fresh hydrogen spills onto the shell makes even more gamma rays. Basically, it's kind of like the death splutters of a car running out of gas. Even though there's less available hydrogen for fusion, the temperature goes up so high that the star is no longer in hydrostatic equilibrium. The fusion is not being balanced by the gravitational pressure, but the fusion is kind of going haywire for a few minutes as the star runs out of fuel. And the extra temperature produces more gamma rays than the gravity can balance, and the outer star begins to expand. Does that make sense? You really have to think your way through this one. It's very complex. Okay, Arunsak, that was a cool discussion. I'm really glad you asked that question. Okay, so now you guys are starting to get, by the way, the one-word answer, Arunsak, that you could have had, I could have given you is, the reason why the star expands is because of hydrogen shell fusion. Shell fusion is different than core fusion. And that's what the book is trying to show you when it shows you this picture here. The contracting helium core, and it's the hydrogen burning shell. It's the shell that's puffing out those outer layers of the star. Okay, let's go back to our graph here. We're kind of running out of time, so I'm screwing this day up here, but let's see if we can just finish this chart really fast, and we'll come back to it after our lectures on relativity next week. Let's see if we can take our last couple of minutes just to clean this up. Wow. I honestly had a lot more to tell you guys, but as usual, not enough time to do it all. Okay. What's going to distinguish the red giant version of a star is that red giants will eventually get their cores hot enough to undergo helium fusion. And when helium fuses, it does not fuse to the next element of lithium. It jumps 3 atoms and it fuses into carbon. So during a red giant phase, all stars, whether they are low, intermediate, or high mass stars, are going to undergo a nuclear reaction sequence, which astronomers call the triple alpha process. I want to tell you about the triple alpha process because I think our first or our second homework question today will be based on that. The triple alpha process. All stars, whether they are low, medium, or high mass star, must undergo this stage of fusion. And by the way, something kind of beautiful about this, carbon, the most abundant elements outside of hydrogen and helium. Actually, can I show you guys? There's a legendary graph. It's known as the cosmic abundance of the elements. And it's really related to the nuclear fusions of stars. Now, this graph will also appear in our homework today, so it's worth us discussing it. 106. This is a plot of atomic number, how massive your nucleus is. Here's hydrogen and up here is uranium, versus how abundant they are in nature. For every 1 hydrogen atom that you find, helium has an abundance of 1/10 that. So you have to count 10 hydrogen atoms to get 1 helium. You guys will notice that the next most abundant elements in the periodic table are carbon, nitrogen, and oxygen. And they have abundances of roughly 1/1000th that of hydrogen. So you have to count 1,000 hydrogen atoms in space before you find 1 carbon. But how would that compare to something like iron? Can you guys look at this graph and tell me approximately how many hydrogens would I need to count through in space before I found one iron atom?
$100,000.
Yeah, because the relative abundance is 10 to the minus 5, right? So it's 10 to the 5 hydrogens to 1 iron. You'll notice that the least abundant elements in nature are the 3 simplest elements that follow helium. Lithium, beryllium, and boron have the lowest abundances of almost any element in the periodic table. And this is actually a big geopolitical issue because most of our lithium today, well, it's mined from salt flats, like the salt flats in Bolivia. And lithium is used, of course, in your iPhone batteries. So there's global strategic wars going on behind the scene between China, the US, and the United States, and Russia, for who can control the world's lithium supply, because then you can control all the technological gadget supply. The reason why these elements are so low in abundance in nature is because they get skipped over in the second type of nuclear fusion that stars undergo. And that type of fusion is called the triple alpha process. I'm going to show it to you and then we'll take a little break here. Can I get a picture of the triple alpha process? We need this for our homeworks today. The triple alpha process is a relatively simple nuclear reaction that takes place in 2 stages. In the first stage, 2 helium nuclei just violently slam together to make an element called beryllium. Beryllium-8, which has 4 protons and 4 neutrons, is an unstable nucleus. It's kind of weird. It has equal numbers of protons and neutrons, but it's unstable. And then the beryllium-8 is quickly whacked by another helium before it can disintegrate, and it then forms the stable carbon-12 nucleus. That means the net reaction for the triple alpha process goes something like this. Let's write it down together, shall we? 3 heliums slam together to make 1 carbon and 2 gamma rays. This gives the stars a second lease on life, and they can exist for another 1 billion years as a red giant. Betelgeuse, that famous star in the shoulder of Orion, is a red giant. Aldebaran is a red giant. Many of these famous red stars that you know, or that you don't know maybe, are red giants. By the way, I'd like to point something out to you guys. According to that graph on the cosmic abundance of the elements, after hydrogen and helium, the most abundant elements in nature are carbon, nitrogen, and oxygen. How many of you have taken a biology class and know what DNA is made out of? Anyone here take a biology class? And my guest knows. My guest Catherine knows that it's deoxyribonucleic acid. Okay, so tell me about those little CATG things. What are they made out of? Did you guys know that? All right. Well, here's the Wikipedia page. Tell me, what are the atoms that make up our DNA?
Hydrogen, oxygen, nitrogen, carbon, phosphorus.
Do you understand my point? What's
No.
my point?
I don't know.
I
So we're
know.
made out
I
of
want
hydrogen
you
and
guys to
oxygen?
leapfrog with me here. I've got a really cool point to make about aliens. Arunsak, stop talking to your friend. I'm trying to tell you about aliens here. Elijah, do you understand my point? Is there anyone out? Do I have any friends? Does anyone
Yes.
understand me? Someone explain my point.
Is it like that we're like made of the same type of thing that stars are?
It's that we're made out of the most fucking abundant elements in the in the whole universe, okay? We are made of the most abundant elements in the universe. If you go floating around through space, you find lots of carbon, nitrogen, and oxygen. So what, you know, last night I watched Alien Covenant in 4K. It was freaking awesome. Like, there are going to be aliens all over the damned universe because the stuff that makes up DNA are the most abundant elements in nature. We aren't just made of uranium or some exotic thing we're not made of lithium. We're made of really common household stellar ingredients. If this shit is floating all over space, the chances that on some planet in some soupy pond, a lightning strike would have sizzled some of this stuff together is extremely high because there are so many stupid stars and so many stupid planets. Anyways, you are made out of the same stuff that gets formed in stellar. Now, there are other nuclear reactions that we have to get to next time, but I've taxed your memories enough for today. So what do you say before we do our homeworks that we take a little pause? You down for that?
Of course.
Okay. So we'll take a 15-minute break or so, and then we'll get back and we'll crank out our homework real quick. Okay. Pausing the video. All right, welcome back, everyone. It's time to bust out homework number 10, which I believe is chapter 17 in the book. How does that look up on Blackboard there? Where are you? Homework 10.
Yeah. It is.
Okay, great. Can you guys read me those numbers in a second when I remember those 43, 49, 50, 51, 54? We can remember that, right? Okay. All right. So let's do all the usual good stuff that we do when we do our homework. Speaker view. Let's get our names on that page. Let's write down AS1020 and your section on that. This is homework number 10. It's chapter 17 problems. What was it? Was it 43? What are the numbers?
43, 49, 50, 51, and 54.
From what I remember, guys, this homework is actually relatively straightforward and quick. All right. So, Christopher, are you down to give us chapter 17, 43? Read that out.
Which one?
Number 43, right?
Yeah. Okay. Rare elements. Lithium, beryllium, and boron are elements with atomic numbers 3, 4, and 5, respectively. Despite there being 3 of the 5 simplest elements, figure 17.15 shows that they are rare compared to many heavier elements. Suggest a reason for their rarity.
Okay. So once again, this is about a legendary graph in astrophysics known as the cosmic abundance of the elements. I showed you a kind of lamer version of it in the slideshow, but there's, if you just type cosmic abundance of the elements, I've noticed on the image search before that there was a couple of very, very nicely done ones. I like this one in particular. Let's just look through this nice and slow. This one's cool. Do we have a higher res version of this? How many pixels is that? 800 pixels. Okay, we can rock that. Okay, let's check this guy out for a second. This shows you all of the elements laid out as a plot where they plot the number of protons on the x-axis. Remember, one atom differs from another atom by the number of protons in its nucleus. On the y-axis, they're showing you the relative abundance of the atoms. They're plotting it in log space. So do you guys know what 10 to the power of 0 is? What is 10 to the power of 0 equal to?
1.
That's 1. What is 10 to the power of 1 equal to?
10.
And 10 squared is 100,
100.
right? So you guys see how this works? This is 1,000, 10 to the 4, 10 to the 5, there's a million, there's a trillion. Now, you guys know that most of the universe, 98%, is in the form of hydrogen and helium. Do you guys remember what the rough fraction of hydrogen to helium is?
So
What
there's 10 hydrogen to 1 helium?
So this is kind of my point. It depends if you do it by number or if you do it by mass. And this subtlety might have slipped past you guys, so we should talk about it. If you do it by number of atoms, there are roughly 10 to 1 or 9 to, oops, I didn't mean to do that. Oh, shoot, okay. It's roughly by number 10 hydrogens to every 1 helium. But you guys remember that helium is 4 times more massive than hydrogen. If you multiply this guy by 4, the ratio by mass is 70% hydrogen by mass and 28% helium. So I wanted you guys to pay attention to that, because if you hear 78% hydrogen to 28% helium, you might naively think that there's roughly 3/4 to 1/4, or actually, I guess it's like 1/3 to 2/3. You might think that it's 2 hydrogens for every 3 helium. The problem is hydrogen is much lighter than helium. So for every 10 hydrogens, and you can see that, you'll notice that hydrogen is close to 10.5 and helium is close to 9.5. So there's roughly a factor of 10 difference between them. As I pointed out at the end of lecture, carbon, nitrogen, oxygen, by the way, here's phosphorus. Isn't that interesting? There's the other part of our DNA. Carbon, nitrogen, and oxygen are like 1,000th the abundance of hydrogen and helium. As you get heavier and heavier up the food chain here, obviously elements like uranium and plutonium and mercury and silver and gold are quite rare. But it's interesting that these 3 very light elements, lithium, beryllium, and boron, have such low abundance. Do you guys remember why they have low abundances? Did you get the takeaway there or what? Oh, there's one last puzzle piece that you might be missing. We know a lot about the Big Bang, the explosion that created the universe. Now, I haven't gotten to this in our lectures yet, and I'm not sure if I ever will. But in the 1960s, 2 famous scientists, Penzias and Wilson, working for AT&T Bell Labs, discovered the leftover glow of the Big Bang, known as the cosmic microwave background. Cosmic microwave background. Because we've studied the leftover radiation from the Big Bang, we know that the Big Bang could only create hydrogen and helium. We have almost 100% certainty on this. When the universe first formed, only hydrogen and helium existed. Do you see all of this other gick here? All of this other gick came from nuclear fusion in the cores of stars. So why are lithium, beryllium, and boron of such low abundance relative to their other compatriots, which are light elements? In other words, what's the answer to the stupid question? No?
I want to
More
guess
clues?
Christopher, could you say that again?
I want to guess that it has something to do with how the little atom bits fit together.
It has to do with one of our types of fusion. But which type? I was going to see here if I could.
Is it the PP fusion?
It's not the PP fusion.
No PP? Dang it.
Proton-Proton Chain fuses hydrogen into helium, right? The proton, I was going to see if I could connect this to the projector so that you could watch it.
Is it the CNO thingy?
It's not. The CNO is also hydrogen to helium fusion. You're still
Is it the
wrong
triple
one.
alpha?
That's right. Why is it the triple alpha process? Why is that what causes those elements to be rare? Why does this reaction in the red giants of stars cause lithium, beryllium, and boron to have super low abundances on Earth?
Is it because, so what is Be? That's boron, right?
No, that's beryllium.
And that's the rare one.
Yeah, you know what? You guys just probably don't know your way around a periodic table of the elements. Let's, here. Periodic table of elements. There's a nice, colorful, non-threatening one that I like.
I was reading that image correctly. So is it because this fusion process also fuses the beryllium and the helium to make like a carbon or whatever?
Right. Wait, can you guys see my, you can't see this, can you? Share screen. Look, let's say we were naive and we didn't know anything about fusion, but we knew that somehow the Big Bang produced hydrogen and helium. We know that in the sun, hydrogen fuses into helium. So if I told you that stars were eventually going to fuse helium as red giants, one might naively think that helium would then fuse into lithium, and that lithium would fuse into beryllium, and beryllium would fuse into boron, and boron fuse into carbon. But that's not how it works. How does it work, Christopher?
Does the helium and the beryllium like smash into each other and make the carbon?
Yeah, basically like first the heliums fuse. You know, how many protons does helium have? 2. So if you add a helium plus a helium, 2 plus 2 equals 4. And then if you add 4 to another 2, you get 6. Maybe we got to draw this out. Okay, so before we can write the answer to this question, there are 2 pieces of the puzzle that you need. First of all, you got to know what the atoms look like, right? So let's draw the number of protons in hydrogen, helium, lithium, beryllium, boron, and carbon. Now, I'm not going to draw the neutrons because I don't have enough room on my blackboard. So I'm going to do 1 proton for hydrogen, 2 protons for helium, 3 protons for lithium, 4 protons for beryllium, 5 protons for boron, and then for carbon, 6 protons. Now let's ask ourselves about the 2 steps of the proton-proton chain. I'm sorry, the 2 steps of the so-called triple alpha process. There are 2 steps in the reaction. In step 1, helium plus helium makes, well, look guys, 2 plus 2 gives you 4 in step 1. So that makes beryllium plus a gamma ray. In step 2, the beryllium plus the helium fuse to make carbon and a gamma ray. So you add another 2 protons and that gets you to carbon. So what's the reason why lithium and boron are so rare in the universe?
Oh, it's because it doesn't add up.
Yeah.
It's hard to get to 3 and it's hard to get to 5.
Well, then
Right.
why would beryllium have such a low abundance? Because you can get to 4.
Because it keeps getting
It's
turned
because-
into carbon.
There you go.
It has the
Chris,
same
you took
fusion.
it from me, dude.
No, that's great. You guys, it's a collaboration, not a competition. Hey, listen, I want to tell you something.
Great
Beryllium,
minds think alike.
exactly. Beryllium is actually a really weird ass element. I want to just quickly divert you to beryllium, the Wikipedia page for beryllium. It turns out that beryllium-8, the one that's created inside of stars, is actually super unstable. For some reason, 2 protons and 2 neutrons is a really stable configuration, but 4 protons and 4 neutrons is not. The only beryllium that even exists on Earth is so-called beryllium-9, which has an extra neutron in it. And beryllium is like this magical gray metal that you can combine with other metals to make super high powered jet engines and things that don't melt under high temperatures. It's kind of interesting. It's a steel gray, strong, lightweight, and brittle alkaline earth metal. In structural applications, the combination of flexural rigidity, its ability to bend, thermal stability, thermal conductivity, and low density make it a desirable element in aerospace materials for aircraft components, missiles, spacecraft, and satellites, okay? So all of that cool stuff that you like to play on your PS5, all right? We could make a Dyson sphere from beryllium. All right, let's write this all into a paragraph now that you guys understand. We'll write it out like this. Lithium, beryllium, and boron have such low, and I guess the way we would phrase this is cosmic abundances. Lithium, beryllium, and boron have such low cosmic abundances because these elements are essentially skipped over during helium fusion in red giant stars. Now we're going to elaborate on this helium fusion to demonstrate our knowledge, all right? During the triple alpha process, which is what this question is really about, during the triple alpha process, two helium nuclei fuse into beryllium-8, skipping over lithium. Beryllium-8, I'll use the abbreviation for it here. Beryllium-8 then fuses with a third helium to make carbon. And in parentheses, we might say +2 gamma rays, but you know, we'll just leave that part out, I guess. 1 second here. Okay. With a third helium to make carbon. Thus, boron is also skipped over. And now we'll address the beryllium issue. Beryllium-8 is highly unstable. It's a radioactive isotope. And also fuses to carbon during the reaction. Leaving it with very low abundances. I don't know if you want to say on Earth or in space. It's the same thing, really. We'll say in space. Okay? Sorry about the handwriting there, guys. Hopefully you can read all that. Take a second to finish that up. Sorry about that. Are we finished? May I erase?
Give me one more second.
Yeah, sure. Just let me know when you're done. How about now? Who was that? Was that Paul, Kevin, or I can't really tell these disembodied voices here.
Whoever was talking, it wasn't me, Kevin.
Oh, sorry, Kevin.
Yeah, that was me. I'm good right now.
All right, awesome. I'm erasing unless there's any objections. All right. That takes care of 43. Arunsak, do you want to read one for us? 1 through 49?
Yeah, I can do that. 49. The title is Escape Velocity from a Red Giant. What is the escape velocity from a red giant with a mass of 1 solar mass and a radius of 100 solar radius? How does that velocity compare with the escape velocity from the sun? Describe how your results help account for the fact that red giants have strong stellar winds.
Okay. A red giant is a super-sized star, but it is not a super-massed star. Remember, the mass of a star is roughly preserved. You're just spreading it out over a bigger radius. What do you think? What do you guys predict? Should the red giant have a larger or a lower escape velocity than the sun?
Lower.
Pardon?
I thought it would be higher.
I want to say like the same because the mass is the same, and the mass comes from the gravity. So
we've had 3 different answers. I actually, that's okay, but that's good. We have 3 different predictions. Kaitlyn, the first time I ever did this problem as a student, I thought what you did. I expected it naively to be greater. Christopher's got an interesting point. It has the same amount of mass, but remember the escape velocity also depends upon radius. Now, who was that said it would be lower?
Kevin.
Kevin has got good intuition. It turns out that you're diluting the gravity by spreading it over a larger radius. It's easier to get off the surface of a red giant than it is the sun. Let's compute why. The escape velocity formula is the square root of 2 times big G times the mass of a star divided by the radius of a star. Let's compute the escape velocity of a sun first, okay? The mass is 2 times 10 to the 30 kilograms, and the radius is 7 times 10 to the 8 meters. Let's plug that into our formula. The escape velocity of the sun is then 2 times big G. Big G is 7 times 10 to the minus 11 meters cubed per kilogram per second squared, times the mass of the sun, 2 times 10 to the 30 kilograms, divided by 7 times 10 to the 8 meters. Go ahead and punch that up for me. I'll take your answer at any moment.
Six times to the 5.
Sorry, I think you forgot to square root, Christopher.
Mm,
It can't be. First of all, you didn't give me any units, so I don't know what you mean by 6 times 10 to the 5.
At 4 to the 11th meters per second.
Hell fucking no. Actually, I think Christopher might have had it right. You know what threw me off, Christopher, is you putting it in scientific notation. That's less than a minute. Do I have to do this? If I have to do this calculation, y'all are fired, okay?
okay, then 600,000. That's what I got.
Yeah.
Uh,
I'm sorry, 600,000 what though, Christopher?
hold on.
Arunsak, you
3
forgot.
meters per second, right?
That's right. Kilograms cancel, 1 meter cancels, and then the square root of meters squared per second squared is meters per second. How many kilometers per second is that?
$60.
False. How many meters?
600.
It's 600 kilometers per second. Let's box that up. That's the escape velocity of the sun. Make sure you get all this down because I'm going to need to erase before I can do the next part. Can I erase? Now, we could plug all this again in to do it for the red giant, but I've got a smoother idea. The escape velocity is radical 2gm over r. All that's going to change is that our radius is growing by a factor of 100. So watch this slick Rick math technique, okay? For the red giant, the velocity of escape is going to be the square root of, I'm just going to write this out symbolically at first. 2 times g times the mass of the sun over 100 solar radii. Guys, how does this calculation differ from the previous one that we just did? By what factor?
The radius, the 100.
But it's not just 100, you're square rooting the 100. And you have to distribute the square root to each term. So let me rewrite this a different way using algebra. I'm going to write this as the square root of 1 over 100. And this is totally valid by the rules of algebra, times the square root of 2 times g times the mass of the sun during the radius of the sun. All I did is I used the associative rule of multiplication to pull out the radical 1 over 100. I basically pulled out the square root of 100 on the bottom outside so that you could see that this here, this is just the escape velocity of the sun, which we just computed. And what did that value turn out to be in kilometers per second?
600.
Right. So what we have is radical 1 over 100 times 600 kilometers per second. What's my final answer?
6,000 kilometers per second.
Jesus, that 100 is on the bottom. What's the square root of 100?
It's going to be 60 kilometers per second.
Yeah, this becomes 1/10 times 600, or 60 kilometers per second. We see that Kevin's intuition was correct. Let's have a statement that sums up what we have learned. The escape velocity of a red giant star is 10 times lower, and we'll underscore the lower because that was the surprise. The escape velocity of red giant star is 10 times lower than a main sequence star, which means that gas and plasma can actually jump off the surface of the star. They call them stellar winds, and can be blown off into space, which means that gas can easily be ejected into space in the form of strong stellar winds. We believe that stars, once they become red giants, become ghost-like tenuous structures that can kind of puff themselves apart into cosmic smoke rings. There's kind of an interesting recent story to this. You guys know about the constellation Betelgeuse. I'm sorry, wow, the constellation Orion.
Constellation.
Yeah, I'm sorry, that was last night's whiskey talking, all right? The constellation of Orion contains a star named Betelgeuse, okay? And Betelgeuse is also known as Alpha Orionis. As you can see in this picture from a long time ago, it's clearly, along with Rigel, the brightest star in the constellation of Orion. You guys probably missed it because you weren't paying attention to astronomy news, but something crazy happened last year, just before COVID. Betelgeuse started spontaneously dimming. Like, I swear to God, guys, last winter, I would go out with my naked eye. I had never seen anything like this in my entire life. Did you hear about that, Christopher?
Yeah.
I would look up at this star with my own eye, and it was dimmer than the stars in the belt. Betelgeuse just suddenly started dropping its luminosity, and it freaked people out because they believed that Betelgeuse might be undergoing a stellar core collapse, and they thought it was about to go supernova. I don't know if you guys understand this, but if this star 600 light years away were to go supernova, it would become so bright that you would be able to see it during the daytime. Like, that would be a holy shit kind of event. If when Betelgeuse goes supernova, you are going to be able to see that thing with your naked eye during the day. At night, it's probably going to be comparable to the full moon or brighter, and you'll cast a shadow in the forest from red light from Betelgeuse. Things are going to be weird when that happens. Pardon?
I said I want to see that.
I want to see that too. I hope it pops in the next 100 years. It would be no human being will have ever seen anything like that before. It turned out though that the reason why it was dimming is Betelgeuse turned out to not be going supernova, but it sloughed off such a big blob of gas that the blob of gas cooled down and blocked some of the light from the star. Basically, essentially what we're talking about in this problem here. In fact, in that regard, Betelgeuse probably looks not like the star, looks less like the sun. Come on, where's my damned? And it probably resembles something more like Eta Carina. You guys might remember that Eta Carina is a star that's exceeding its Eddington luminosity and kind of blowing itself apart. I bet if you could resolve Betelgeuse more carefully, you'd actually see that it was not quite this crazy, but in the process of puffing off some of its outer layers of gas. That star is shining itself to death and blowing itself apart. One day, yeah, that is bad. One day our sun will do this. And do you want to know what it's going to look like maybe 100 million years after that? It will turn into this. This is another beautiful thing that we see in space. It will turn into the Ring Nebula. This is what a star looks like long after it's puffed itself apart. It actually blows off its outer envelope and it condenses into a beautiful ring of gas, something like this. We'll talk more about those later. That's what Betelgeuse is going to look like a few 100 million years from now. Yeah. These nebulae are the death. You're catching the graves of stars. They're basically like these expanded gas clouds. It's quite nice. All right, you'll learn more about that a week from now. Let's move on to the next problem here. So we got 43 down the hatch. We got 49 down the hatch. Who's next in my boxes there? Stacy, would you read me number 50, please? Can I erase? I'm doing that. Oh, Emily needs more time, so let's give her a second. I'm going to get a glass of ice water. Jerry said, I've got 3 more problems. I deal with that. It'll just be like another 15 minutes. I'm a little hungry. Are you? Look at that little nibble. We can wait for Brody to go to Plant City, but we'll make it to a little small. You guys want to go to Plant City?
Eventually, yeah, let's talk about it.
All right. All right. Can I erase now? All right. Thanks, Emily.
Professor?
Yeah.
If I buy a telescope, would I be, I mean, I live in Providence. I imagine it's going to be like super polluted, the air. Can I see anything?
You sure can. You can see awesome stuff no matter how light polluted. Now listen, Arunsak, I've got this big ass telescope that I got CCRI to buy me. It's an 8-inch telescope, and these things are quite expensive, but they're amazing. What really happens with a telescope is if you get a big enough telescope to make it fun, it's kind of a lot of work to set it up. So unless you're really, really into it, or unless you're doing it with a friend, you might not set it up as much as you want. Now, a cheapo telescope like this little doinker here, you can see some craters on the moon with it, but you're not going to be able to see the Ring Nebula. You need to like at least maybe a 6-inch or an 8-inch telescope to see the Ring Nebula. I show people the Ring Nebula all the time, but those can come, they can be a couple of $1,000s. Arunsak, a great way to start your journey that's very inexpensive if you want to get into telescopes and stuff is, and you know, someday when the class is over, if we can figure out a socially distanced appropriate way to do it, I might be down to invite a couple of you guys to the Peerless Roof downtown, and we can set up that 8-inch telescope and let you take a peek. Now, I'm not supposed to be doing that officially at the observatory because of COVID, but if I, as a personal citizen, want to show my friends a few objects in space, there is nothing that prevents me from doing that. Okay, so we We could talk about that if enough of you are really jazzed about this. I'm open to like a session one night. But let me show you another solution, Arunsak, up here. A great way to get going in astronomy, you can do this. It's always personal with me, pal. You can buy a pair of badass 20 by 80 binoculars. Like any bigger than this, you need a tripod, okay? And these big badass binos are great for looking at open clusters. And if you're in a dark enough sky, globular clusters. The reason why these big honkers are so much fun is, first of all, you can get a decent pair for like $100, and they're portable. So you can just strap the thing around your neck. And if you go on a camping trip or you're out in a field with your friends, you just sit back, put your lawn chairs down, and you can just look all throughout space and you can see so much cool stuff. You wouldn't believe how much range you can get out of a good pair of binos. And then when you do go to a dark sky, it's easy to set up and take down. They're not a pain in the butt. So Arunsak, I think your gateway drug into telescopes should be to buy a pair of 20 by 80 binoculars. And as an example of how you do that, if you ever decided to do that, you would just go to like eBay, or you could go to Amazon, right? eBay is cool because you might find a used pair on the cheaps. And then we'll look up astronomy binoculars. And you'll see, like, you know, I would actually splurge and at least, look, get one like this. 100 by 180, like that's $50. So that's something that's, of course, the more money you spend, the better the quality of the optics will be. In general, you want the barrel to have the biggest diameter possible. I would type in astronomy binoculars. Let's do 20 by 80 maybe. Usually the first number is the diameter of the lens, and the second number is the magnification. Look at this. Oh, wow. You can see that sometimes the prices can be astronomical, okay? So this is a serious pair. This is a funsy pair. Okay?
Oh.
Yeah. Let's check out what I think Meade went out of business. What about like you know, it would be like really sick, a 10-inch Schmidt-Cassegrain telescope. Let's okay. SCHMITD Cassegrain. So if you want to get, look, I mean, sometimes people will sell this. That's actually a decent price for a 10-inch telescope. That's the same one that I have. That's $1,000. So I don't know, you know, how much money is in your piggy bank, but astronomy can be a very expensive hobby. It is cool. This you can see the Ring Nebula with. This is what my telescope looks like. Okay. Stacy, you're up for problem number 50.
Okay. It's roasting the Earth.
Nice.
During its final days as a red giant, the sun will the sun will reach a peak luminosity of about 3,000.
3,000 what?
Luminosity sun.
Solar luminosity units, but okay, fine.
Thank you. Earth will therefore absorb about 3,000 times as much solar energy as it does now, and it will need to radiate 3,000 times as much thermal energy to keep its surface temperature in balance. Estimate the temperature Earth's surface will need to attain in order to radiate that much thermal energy. You will need to use the formula for emitted power per unit area in Mathematical Insight 15.5.
Okay, let me translate all that into, well, plainer English anyways. Let's draw a cartoon together. First, let's draw a big swollen red giant sun. And then let's draw an unhappy roasting Earth. Okay, this red giant has more surface area, and so it's pumping out 3,000 times more light than it does today. And that means the brightness of the red giant will be 3,000 times a number that we calculated earlier in our class called the solar irradiance. That's the number of watts per square meter that the sun impinges upon Earth. Here's something that you might not think about. Planets need to be in thermal radiative equilibrium, which means if the planet absorbs 3,000 times more sunlight, it eventually must re-radiate that sunlight. And this is actually true of the Earth today. The Earth re-radiates approximately the same amount of light that it receives from the sun. Let's imagine what would happen if it did not do that. If the Earth did not re-radiate the same amount of light it receives from the sun, then it would gain internal energy over time, and the Earth would be like an energy destroyer or something. That doesn't make any sense by the conservation of energy. Likewise, if the Earth pumps out more energy than it receives from the sun, then it's got to be generating energy in its interior. But we know the Earth does not have a high enough central temperature to create nuclear fusion. The only logical conclusion is that if the Earth absorbs 3,000 times more sunlight, it must then re-radiate that sunlight as a black body. And what's the formula that tells us the amount of radiation that a black body gives off? Based on its temperature. No? Where's our formula sheet? Do we have a formula sheet? Some of you taped it to the wall, right, Stacy? Was it you, Stacy, that taped it to the wall?
Yeah, I did.
Christopher Leonard, you could raise the people have been trying to raise temperatures high enough for fusion for years. The NOVA project in France uses a whole bunch of high-powered lasers to compress a deuterium pellet, and they're trying to generate artificial fusion so that we could power the Earth's energy needs just like a star does. That's a big topic of conversation. Anyways, what's the equation that we need here? Do you guys remember? The brightness of a black body based on its temperature. Not Bohr's. Niels Bohr.
Boltzmann.
The Stefan Boltzmann law. Now, they want us to compute the temperature of this new Earth. We can only do that if we know the brightness of radiation on its surface. Luckily, we can calculate that with the inverse square law. The brightness of our red giant will be 3,000 times the luminosity of the sun over 4 pi d squared. D will be the distance from the red giant to Earth, but we'll just pretend like it's 1 AU, because basically it's 3,000 times brighter than the sun is today. The luminosity of the sun is 4 times 10 to the 26 watts. And do you guys remember how many meters it is in 1 AU? Not kilometers, but meters. Otherwise, I'm going to make you do some dimensional analysis.
7 times.
Sorry?
I'm thinking. I was trying to change my mind.
Yeah, that was you were mentioning the radius of the sun, 7 times 10 to the 8 meters. This distance from the center of the sun to Earth is 1 AU. How many kilometers is that? Really? Jesus. How many kilometers in an astronomical unit? I would have thought you guys memorized this by now, just by accident. Okay, look it up.
One 1.5 times 10 to the 8
What units?
kilometers in 1 AU.
I prefer to write it as 150 million myself, but you're not wrong. Okay, Christopher, how many meters is that?
It's 150 times 10 to the 9, so that'd be billion.
That's right. 150 billion meters squared. Go ahead and punch that into your cal keys for me. Punch them up.
Four million watts per square meter.
Jeez Louise. Did anyone else get that?
Yes.
Cool. That's certainly a lot more than the 1400 watts per square meter we get today. Let's compute what the temperature of this Earth would be if it then has to re-radiate that 4 million watts per square meter. The temperature will be the fourth root of brightness over the Stefan-Boltzmann constant. I'm running out of space here, so this will be the fourth root of, this is getting messy. You know, I don't like this. I'm gonna go up here, okay? Temperature is the fourth root of brightness over the Stefan-Boltzmann constant. The brightness is roughly 4 million watts per meter squared. The Stefan-Boltzmann constant is 6 times 10 to the minus 8 watts per meter squared per Kelvin to the fourth. You all know how to do that fourth root thing, right? Go ahead and punch them up. I told you about the shoe shine guy who sits in the corner downtown, right? Shine him up. That's what he says.
3000 Kelvin.
3000 Kelvin. Hey, Christopher, how do you feel about living on a planet whose average surface temperature is 3000 Kelvin?
The heat already makes me want to die, so that would be
Today, the average temperature of Earth, if you average from the North Pole to the equator, is, oh my God, why am I forgetting this? It's 15 degrees Celsius. Well, it's rising because of climate change, which is totally real, by the way. 15 degrees Celsius, we have to add 273. Sorry, we have to add, yeah, negative 273 is, so plus 273 is 370, sorry, 283, 288. Right? Did I do that right? The average temperature on Earth today is about 288 Kelvin, if I did my maths correctly. A future Earth will probably, let's get a weed smoking artist picture here. This is what it will look like on a future Earth, where the sun turns into a red giant. The oceans will boil away. That's well above the boiling point of water. Probably some of the volcanic rock and the granite will start to melt. Either you'll have a partially liquid surface, a molten surface, or it might be like sticky tar. All organisms will be burned to a crisp. Wood would ignite at this temperature, right? Hell, probably the whole atmosphere will set on fire first. Thems will be that's some Revelations kind of Armageddon, right? That'll be pretty wild. Okay. You guys got all that? Emily, can I erase? I don't even know if yeah, okay. You're hiding on us today, Emily. You've been demoted to troll status. Kaitlyn, can I call on you to do number 51?
Yeah, let me pull it up.
All right.
This is homework, right? Not a lab?
Yeah, this is homework. Homework 10.
Yeah. What number were we on again? I'm sorry.
That's all right, 51. We're on 51.
50. Okay, supernova Betelgeuse.
Oh, cool. Man, this homework is awesome because it ties into everything we talked about today.
Yeah, we mess with it.
Yeah.
Do you want me to read it now?
Hold on. Betel, T-E-L-G-E-U-S-E. Okay, now I'm ready.
Okay. The distance of the red supergiant Betelgeuse is approximately 600 light years. If it were to explode as a supernova, it would be one of the brightest stars in the sky. Right now, the brightest star other than the sun is Sirius with a luminosity of 26 solar luminosity and a distance of 8.6 light years. How much brighter than Sirius would Betelgeuse supernova be in our sky if it reached a maximum luminosity of 10 to the 10 solar luminosity? I don't know how to read that, I'm sorry.
Solar luminosity units or solar luminosities. I'm sorry, what did they give us as the brightness of Sirius? Was it 26 solar luminosity units?
Yeah, correct.
Okay. So Betelgeuse as a supernova will still have a distance of 600 light years, but its luminosity will jack up to 10 billion suns. Sirius is the brightest star in the sky today, 26 solar luminosities. And what was the question again at the end?
One sec. Okay, question at the end was, how much brighter than Sirius would Betelgeuse supernova be in our sky if it reached a maximum luminosity of 10 to the 10 solar luminosities?
Do you guys know what formula we need to do this problem? This is the question you have to ask yourself during, oh yeah?
Yeah, the Stefan-Boltzmann law still?
No, that's if you want to calculate brightness based on temperature. Sorry. Wow, guys, I just did a dumb over here. This is not a brightness, this is a luminosity. I'm sorry. How do we get brightness when we have luminosity and distance? This is the brightness of a star on our sky.
Hold on. I have it somewhere.
We used this in our last problem. Same formula from the last problem.
Inverse.
Square unit law thing?
Inverse square law.
Yeah.
The inverse square law allows us to find the brightness of a star on our sky. Remember that because I'm going to ask you to do these calculations on your exam. Now, I can think of two different ways to do this problem. We could substitute in the values in watts and meters, and then we could divide them. Or if you guys want to do the speedy, quick, slick method, you want to do the speedy method, Kaitlyn?
Yes.
What if we take the ratio algebraically and then substitute in the relative luminosities and the relative distances? In other words, we won't have to convert to MKS units if we set it up like so. The brightness of Betelgeuse, which we're assuming is going to be brighter than the brightness of Sirius. Oh my God, people are killing each other up there. Okay, first it would be the luminosity of the supernova over 4 pi times the distance to Betelgeuse squared, all divided by the luminosity of Sirius over 4 pi times the distance to Sirius squared. Where in order to distinguish the two distances, I've used d sub b and d sub s to represent Betelgeuse and Sirius respectively. Could you guys help cancel out some common terms and tell me what that will reduce to? Let's see how good you are.
Just
Sorry, say that again.
I'm trying to figure out how to word it.
Which terms can cancel out? Which factors rather can cancel out? Factors are multiplied.
4 pi d squared.
No, those are different d's. That's why I made it d sub.
Oh, that's a d.
Look, this
Okay.
is d sub b, and this is d sub s, right? The 4 pi's definitely cancel. So Arunsak, you're usually our algebra whiz. How do you do this then?
Looks like 4 can go, 4 down there can go, pi can go, pi can go. And then the squared can go on the d's.
Oh, no, you can't cancel out no squares.
No?
Have you ever heard of PEMDAS before?
My bad.
Wait, but couldn't you like square root the whole thing to get rid of those?
We're not going to square root. We're going to leave it that way. But a classy thing to do, Christopher, is to take the ratio of the luminosities and kind of segregate them from the ratio of the distances. This is how I would do it if it was up to me. I would write it as the ratio of the luminosity of the supernova to the luminosity of Betelgeuse. And let's say we want to be real tricksy here. Do you guys remember that the bottom of the top goes to the bottom and the bottom of the bottom goes up to the top? I would then reorient this. So I had the distance to Sirius over the distance of Betelgeuse. And rather than squaring them both, to make it even more elegant, I would factor out the square. Now that's class. That is algebraic style, okay? Pinkies out. Now we can simply, since these are ratios, we don't need to actually use our bloody, we don't have to convert to watts and meters. We can just take the ratios of the numbers. So we have 10 to the power of 10 over 26 times the square of 8.6 divided by, or sorry, times 8.6 over 600 square thereof. Punch them up. Come on, buddy.
Is this the only part of this problem?
Yeah. You like that?
I do. I'm just almost out of page. Almost out of room on this page.
Wait, okay, hold on. Question: is that 10 to the power of 10 or 10 times 10?
Okay.
10?
That I was testing you there, Christopher. That was a secret test I was playing on the whole class. When you enter in 10 to the power of 10, it's 1 times 10 to the 10. So you got to go 1 exp10. You do not go 10 exp10. Did you follow that, Caitlin? Caitlin, you've actually made this mistake before, and you don't remember it, but I do. I remember one day, Caitlin, you did 10 exp10 or something. Don't do that anymore, okay? I'm waiting.
Okay, I got 80,000.
Yeah.
Yes, sir.
I'm just testing it again. Yeah, that's what I got too. I'm gonna just do that on the calculator for the benefit of night students who are confused. I did it as 1 exp10 divided by 26 times, open parentheses, 8.6 over 600, close parentheses, square equals 80,000 times. What are my units?
Don't you not need one for a ratio?
That's correct. I was testing you. There are no units. So what does the 80,000 mean, Caitlin?
80,000 times brighter than Sirius.
Right. When Betelgeuse goes supernova, it'll be 80,000 times brighter than the brightest star in our sky. That is shitty bonkers. Okay.
Wouldn't it be a whiteout on Earth then? But it might be too far away, honestly.
Yeah. So it's about brightness, right? So I guess the real question is how many times brighter is the moon than Sirius? The moon doesn't blind you. How many? Let's see if we can answer this. Times brighter is the moon than Sirius? The moon is 63,000 times brighter than Sirius. So Betelgeuse will be slightly brighter than the full moon.
It said fainter.
Well, that's the way the
Yeah, how can the moon be brighter than a
brighter than what?
He meant.
Why are you confused?
It's saying the moon is brighter than the star.
He just meant to say fainter, but he's right in the fact that it'll be slightly larger than the full moon.
I did that in my head, right? So yes, I didn't. I was jumping 2 stones at a time. You were jumping a half a stone at a time, right? So this is a question of magnitude. I'm assuming they asked how many times. Let's see what the question is. Bloody hell! I assumed I knew what the question was.
You just worded it wrong when you searched in Google. It should have been how many times brighter is Sirius than the moon, but instead you put moon than Sirius.
Oh. Okay, that's my bad. Wait, no, the moon is brighter than Sirius, right? Why did I did not write that wrong.
I think your calculation was right the first time, slightly larger than the full moon. I don't know.
Maybe like
Sirius
from
is brighter
Earth.
than the moon. That was
I
our
think we're
question.
all
How
thinking
many
about
times brighter?
separate.
Okay, let's do it this way. It tells us here in this math fact that the sun is 400,000 times brighter than the full moon. I know that the sun is 1,400 watts per square meter. So, so 14, that's the sun. And I'm going to divide that by 400,000. The moon gives off, 4 times 10 to the minus 3. My calculator is fading here. Hold on. That's the number of watts per square meter that the moon gives off. Now, I remember from a previous calculation that Sirius is like 10 to the minus 8 watts per square meter. So if I divide that by Sirius, 1 exp minus 8, the moon is roughly, yeah, it was correct. The moon is maybe, oh wow, that says the moon is 400 times brighter than Sirius. All right, maybe Betelgeuse won't be brighter than the moon, but it'll be comparable to the brightness of the moon, right? Let's not get lost in the sauce here. The answer is that'll be bright enough to see during the day. 80,000 times brighter than Sirius. It won't be as bright as the sun. Maybe it'll get close to the brightness of the moon. In any case, it will be awesome. And so we're finishing this homework. One more to go.
Okay, hold on. But would apparent magnitudes be able to like show the relationship?
Yeah.
Because I did.
Magnitudes are logarithmic, right? So the formula that you already know, you know this formula, that the ratio of the brightness of object 1 to object 2 is 100 to the power of the change in magnitudes divided by 5. So what is the difference in magnitudes?
All right, so the full moon is a -11,
Okay.
and then Sirius is -1.46.
Let's just call it 1.5. So it's -1.5 minus -11. So, shit, I need more arms here.
That'd be 10.5, right?
This would make a good test question. Maybe I'll do this to you. -1.5 negative, basically plus 11. So there's a 9.5 magnitude difference divided by 5, 100 to the power of 1.9. Oh, that was for the moon in Sirius, Christopher?
Yeah.
The moon is 6,300 times brighter than Sirius. That means Sirius would be brighter than the full moon. That's pretty badass. Nice. That's actually a lot brighter than the full moon, isn't it? That would outshine the full moon by a factor of 10. Now, I don't think that's enough to turn the sky blue or anything, but I think it's enough to freak people the hell out, that's for sure. The news trucks are going to be coming around for a statement on that day.
Okay, based on our last problem though, would that like affect the temperature on Earth?
No, but you want to know what's messed up, Christopher? What if a closer star to us went supernova? What if like Betelgeuse hadn't been 600 light years away and had only been like 10 light years away? If we had been located close enough to a supergiant star and it went supernova, it's possible that the entire Earth could suffer catastrophic consequences. I'm sure somewhere out there in the history of the galaxy, at one point in time, since the Big Bang, there has been a planet that just got wiped out by a supernova. Think about how wasteful nature is. She'll spend all this time building up a planet full of little bunnies and ducks and pigeons, and then suddenly, poof, it's all gone. That gives you something to think about.
Gotta humble those little meat sacks.
Considering that your Instagram handle is, what is it again? I'm starting to get worried about you, Christopher. All right, let's get number 54 done, and then I can hang out with my buddies and play my show. Stacy, can you do that for us?
Sure, hold on one second. 54. Oh, I'm not worthy.
Oh, you can't do it? All right, does anyone else have it handy? What would help here? It can be anyone.
Yeah, sure.
Thanks.
54. The algal binary system consists of 3.7 solar mass units, stars. Okay, a star that is 3.7 solar masses, and a star that is 0.8 solar masses, with an orbital period of 2.87 days. Use Newton's version of Kepler's third law to calculate the orbital separation of the system. How does that separation compare with the typical size of a red giant star?
Okay, to make this problem real fast, we'll use the kiddie edition of Newton's version of Kepler's third law. The kiddie edition tells us that the total mass of my binary in solar mass units is simply a cubed over p squared, where we're going to use Keplerian units, if you know what I mean there. Arunsak, you want to help us do some algebra? See if you can solve that for A in one shot in your mind.
A equals cubed root of m over P
No,
squared.
P's got to go up next to the M, right?
Okay, M times P squared.
That's right. The total mass times P squared. But P needs to be in years. So Arunsak, while you're at it, why don't you help me convert from days to years real fast?
365, 1. 1 at the
Okay.
top.
Plunge it and give me 3 sig figs. 3 sig figs.
0.87 divided by 365. 7.86 to the -3, which is times 10 to the -3.
Yep. Okay. And what do we get if we add 3? Well, here. So A is just going to equal the cubed root of 3.7 plus 0.8 times 7.86 times 10 to the -3. And I'm leaving the units off because this is a magical formula that just kind of works out to be an AU.
Uh, 0.3
0.3 what?
AU.
Good. Now, that's roughly the distance that Mercury orbits the sun. So these stars are certainly close. But you start to realize that things are weird when you realize that one of these stars is a red giant. What is the typical radius of a red giant? In our previous problem, we saw that red giants typically have radii of 100 solar radii. Let's convert using dimensional analysis from AUs to solar radii, and Kaitlyn, you're going to be my guinea pig for that, okay? So Kaitlyn, help me do dimensional analysis. We're going from AU to solar radii. How do I begin?
Oh crap. Okay. You want to start with an X bar?
Well, first you have to write down what you want to convert, right?
Okay. 0.3 AU.
Okay. And now
X bar. Yeah, and I forgot my conversions. So.
Let me give you a hint, Kaitlyn. You're going to have to do 2 conversions here.
Right, and I don't remember which ones they are. So.
You're going to have to go AU to something, and then something to solar radii.
Yeah, where's that? How do I get to that thing? That conversion sheet.
The conversion sheet.
Yeah.
Well, I told you guys I was going to put it up on Blackboard, and I never did I?
Because you lied.
I lied. I'm liar. The fastest way is for me to just send here. Boom. I just sent it to the whole class through the chat log.
Yeah. Okay. Thank you. Thank you.
I think it has at least AU to kilometers, right?
AU to kilometers, and then kilometers to meters.
No. What? I at some point I gave you
solar radii. Oh my God. I'm sorry.
That's all right.
Yeah, that's it. Put 1 on the bottom, and this doesn't want to pull up for me, so that's
Oh, it's not working?
fine.
I thought you guys might remember it from a few moments ago.
Nope. Goes in, goes right back out, man.
Well, that's why I'm making you guys look it up. The more you look it up, the more likely you are to accidentally remember it in the future.
Here we go. That's what we like to see. Okay. So you're gonna put 150 times 10 to the 6 km.
Okay.
And then you're gonna put 1 on the bottom again.
Love it.
And I don't know what goes on the top.
What is the radius of the sun? Well, one solar radius is how many kilometers? Here we're gonna have to flip it because usually, unless the radius of the sun is less than a kilometer, which would be silly, right? It's 700,000. I'm gonna put you out of, I'm gonna put me out of your misery. Okay, that's what I'm gonna do here. All right.
You should have known. You shouldn't have called on me for all this.
All right.
Yeah, 700.
Punch him up. That's 150, by the way. Times 10 to the 6.
55 solar radii.
What does that mean? What does this mean versus this mean, Christopher?
It's about half the radius of the average red giant.
So if these guys are a binary, what the hell would that look like?
It would look like just one red giant.
Yeah, or even like one of the stars could potentially possibly get swallowed by the other star.
Yeah, I was gonna say kind of like conjoined twins or something. They kind of morph.
like a rotating peanut. And this is what is known in astrophysics. They play an important role in stellar evolution as a high mass transfer binary. Sometimes stars start off like twins and they end up merging into a singleton. Yeah, not too bad, right? Because they morph together and they just kind of, they like fuse together. And that can affect the rate at which the star evolves too. And with that, friends, oh, I don't really feel like saying anymore, so just put an exclamation point. And write down high mass transfer binary and draw the little picture, and that'll be our description. And with that, you have completed homework number 10.
I gotta go, Professor. Thank you.
Yep. Guys, don't forget to submit right away. And one day I'll actually grade all these papers, okay? We'll see about it. Does anybody else
Peace
need
out,
extra-
friends.
Yeah, bye.
Bye, guys.
Does anyone need extra time or can I stop this here?
Bye.
Bye, Caitlin.
Bye.
Christopher, you good? All right.